Let me share the screen. So you may remember yesterday we were discussing about the definition of the reciprocal scaled lattice. And we made a comparison between this construction and the relation that occurs between time and frequency in the Fourier transform of functions that depend on time. So you may have a question. When you consider the function that depends on time, and this function is periodic of some period t, you simply define the frequency as the inverse of t. So you take frequency equal to 1 over period. In the case of a crystal that is periodic in space, we have a periodicity along the first direction with a period equal to A1. Then we have a periodicity along the second direction with a period equal to A2 and so on. So why don't we simply take B1 equal to the inverse of A1 and A2 equal to the inverse, B2 equal to the inverse of A2 and so on. Should be simpler. Actually, the answer is we cannot do it in general because the characteristic vectors A1, A2, and A3 are not mutually orthogonal. Only in the case where they are mutually orthogonal, we can simply take the modulus of B1 equal to the inverse modulus of A1 and so on. But in the other cases, we cannot, and we shall see an example in a second. Okay. So we must, in general, consider the definition of the B vectors as the vector product of two A vectors divided by the volume tau L of the elementary cell. Now let's take an example. We take any vector L. You remember vectors L are those with the integer coefficients in the direct lattice. So they are translational vectors of the direct lattice. And then we take any G. You remember that G is any translational vector of the reciprocal scaled lattice. And then we take the scalar product of the two. Of course, we expect that this scalar product be a number because L has the units of length and G as the units of the inverse of a length. But we just use the definition. You remember L is a linear combination of A1, A2, A3 with integer coefficients of the vectors A1, A2, and A3. And G is a linear combination, again, with integer indices that we call n1, n2, n3 of the vectors 2 pi b1, 2 pi b2, 2 pi b3. So when we take the scalar product of the two, we have a double sum because we have to sum over the index I of the first vector and also over the index S of of the second vector. So we have a double sum whose indices go from 1 to 3 of the individual components that are mi, ai, scalar product, ns, 2 pi, bs. Okay, but then you remember, when you take the scalar product of any vector A times any vector B, you obtain a Kronecker delta of the two indices. So you can rewrite this expression. You bring the 2 pi outside of the sum. So you have the double sum of mi times ns times the Kronecker delta of the two indices is. And you remember the Kronecker delta is equal to 1 when the two indices are equal to each other and is equal to 0 otherwise. Okay, so all cases in which the two indices are different give a 0, so they do not contribute to the result. So eventually we have a simple sum instead of a double sum, with I going from 1 to 3 of mi and I. Obviously, mi is an integer, ni is also an integer, the product is still an integer, the sum of these integers is still an integer. So this sum can be called capital M. So the scalar product of any L times any G is equal to 2 pi times an integer. Now let's take the exponential having an argument like this. It's the imaginary unit J times G scalar product times any vector of the direct lattice R plus a translational vector again of the direct lattice. Okay, then you can split the exponential into the product of two exponentials, and the portion of the exponential with jg dot L, you remember, gives you j 2 pi times an integer. But obviously this exponential is equal to 1. When you have the exponential of 2 pi an integer times j, this is always equal to 1. So the conclusion is that the result is exponential of jg dot r. Okay, you can easily see that this function exponential of jg dot r is periodic in the direct lattice, because if you take r plus a period, any period L, the function does not change the same value. Okay, so this function is periodic thanks to the properties of the vectors A and B of the lattice. Okay, so we have the possibility of using this function to obtain a Fourier expansion of some other function that is periodic. Okay, so consider any function capital F that is periodic in the lattice. That means that F calculated at R plus any translational vectors is equal to F calculated at R. Okay, so F is a function that is periodic in a non-orthogonal space, because the crystal is a non-orthogonal space, but it is still periodic. Okay, so we can expand into a Fourier series this function, and the expansion, as you remember, adopts a set of functions like those exponential that we have examined before that are periodic in the R space. So the expansion is a sum over some index G of some numbers that we call Fg, that are the coefficients of the expansion, times this exponential. So this is the Fourier, the generalization of the Fourier expansion in a non-orthogonal case. What is G? This index G. You remember we must sum over this vector G. This vector is a linear combination with integer coefficients of the characteristic vectors of the reciprocal scale lattice. So we have to sum over the coefficients. And the coefficients are three integers, n1, n2, n3. So as you can see here, the sum over G actually means sum over a triple sum over n1, n2, n3, where these three numbers are integers and go from minus infinity to plus infinity. Okay. What is the form of the coefficients f, g? It is the typical form of the Fourier coefficient. We take the Fourier transform of the original function f over a period of R, but you remember the period of R is the elementary cell. So the integral should be carried out over the volume tau L of the elementary cell. It doesn't really matter which, because of the periodicity of the original function f of R. Okay, so we take the integral over any cell of the lattice and then we divide by the volume tau L. And this is the Fourier coefficient, as you may well remember. We may do it also the same process in reverse. It may happen that we have to deal with functions that are periodic in the scaled reciprocal lattice. So they are periodic with respect to k, because you remember that k is the vector, any vector of the scaled reciprocal lattice. Okay, so by the same construction as above, you demonstrate that the exponential of JL dot k is periodic with respect to k. This meaning that if we add to k any translational vector g of the reciprocal scale lattice, this function, this exponential, does not change. So when we want to consider a function that happens to be periodic in the scaled reciprocal lattice, like this phi, okay? Phi is periodic, we can expand phi a series. In this case, the sum is over L, so it is again a triple sum over the indices M1, M2, M3 of the translational vector L of some coefficients phi L times the exponential, and the coefficients, as usual, are the definition of the Fourier coefficient. We take the original function phi multiplied by the exponential of minus j L dot k, and then we integrate over the elementary cell of the scaled reciprocal lattice, and we divide by the volume tau g of the cell. Okay. This explains why we need this type of construction in a lattice. Okay, and then we now start examining an important type of lattice. It is important because the typical semiconductors that are used in the manufacturing of the electron devices are based on materials like, for instance, silicon or germanium or gallium arsenide, whose lattice is of this type. So we now go over and examine some properties of the so-called cubic lattice. A cubic lattice is a lattice in which the characteristic vectors A1, A2, A3 are mutually orthogonal, and they are also of equal length. Okay, so this is a very special type of lattice, and it happens that, for instance, silicon and germanium and gallium arsenide have this type of lattice. So now we have to learn how to describe nodes, crystal directions, and crystal planes in general in lattices, but in particular in this type of lattice. Okay, so if you look at the upper left part of the figure, this cube here, okay, this is a cube in which vector A1 is aligned along the x-axis, vector A2 is aligned along the y-axis, and vector A3 is aligned along the z-axis. And we have chosen the units in a way that the length of these vectors is equal to 1. They are of equal length, and we set the units so that the length of A1, A2, and A3 is equal to 1. Okay. Then we fix arbitrarily the origin in one node of the lattice. So this point here, 0, 0, 0, is the origin. And this point, 1, 0, 0, corresponds to the length of A1. So A1 lies along this segment here. So the coordinates of this point, of course, are 1, 0, 0. Then A2 lies along this segment, and the coordinates of the tip of A2 are 0, 1, 0. And finally, we have 0, 0, 1. And of course, in this cube, you can define other nodes like 1, 1, 1, that is the one opposite to the origin, and so on. Okay. In space, you can define any point. So for instance, the midpoint of this segment here has coordinates in which the 1/2, obviously, the second coordinate is equal to 1, and the third coordinate is equal to 0. Okay, so this is a point that written there just as an example. Okay, so nodes are indicated with just triplets of numbers that are, of course, integers. Okay, they may be negative if you consider the negative part of the axis. Okay, the sum of the coordinates of the nodes become negative. There is a particular notation that is used in crystallography in which it is preferable to, if there is a minus sign, it is preferable to place the minus sign on top of the number instead of putting it on the left of the number. Okay, in this figure, this scheme is not adopted, but in some books, or in the majority of the books, it is adopted. Now we go to the upper right part of the figure, in which we have a description of how the crystal directions are described, okay? So consider, for instance, this example. You want to describe the crystal direction that goes from the origin, 0, 0, 0, to this point, 1, 0, 0. And you want to incorporate in the description also the orientation from the origin to this point. So the rule is very simple. You again indicate a crystal direction with a triplet of numbers, of integer numbers. And then you place these three numbers into square brackets, like you can see here. Okay, so how do you obtain these numbers? What you do is that you look at the first coordinate of the last point, so 1. And then you subtract the first coordinate of the first point, that is a 0. 1 minus 0 gives you a 1. Second coordinate minus the second coordinate, 0 less 0 is 0, and the same for the third coordinate. So this 1, 0, 0 in square brackets indicates this crystal direction from the origin into the first node. Let's take another example. You want to describe the crystal direction that goes from the origin again to the vertex of the cube that is opposite to the origin. So it goes from 0, 0, 0 to 1, 1, 1. Okay. If you repeat the construction, you have 1 minus 0, 1 minus 0, 1 minus 0. So you have 1, 1, 1 in square brackets. So the direction that I'm pointing with the mouse that goes from the origin to the opposite vertex of the cube is 1, 1, 1. It is easily found that the direction from the origin along the y-axis in the positive direction is 0, 1, 0. And also that the direction that goes from the origin to the first point in the positive direction of the z-axis is 0, 0, 1. Okay, remember these important directions: 1, 0, 0, 0, 1, 0, 0, 0, 1, and 1, 1, 1, because we shall find them again when we shall deal with the properties of silicon. Let's take another example. We want to define the crystal direction point of this side, the point whose coordinates are 1/2, 1, and 0, to the vertex here of coordinates 0, 0, 1. So what you do is, as before, you take the first coordinate of the second point, 0, and you subtract 1/2. So you obtain minus 1/2. Then you take the second coordinate and you subtract from this 0, you subtract 1, so obtain minus 1. And finally, you do the same with the third coordinate, 1 less 0, you obtain a 1. Okay, so it looks fine, but there is a problem that when you do 0 minus 1/2, you obtain minus 1/2, and that is not an integer. And when you deal with crystals, you should avoid integers, okay? Non-integer numbers, okay? People dealing with crystals love only integer numbers, okay? But it is very easy to fix the situation. You just multiply all indices by 2. So minus 1/2 becomes minus 1, as you can see in the figure. Minus 1 becomes minus 2, and 1 becomes 2, okay? And in geometry, you remember, if you have the description of a straight line in space, if you multiply suitably all coordinates by the same number, you obtain the same direction. So obtain another straight line that is parallel to this, okay? And of course, it is equivalent to the original one, okay? So when you find non-integer numbers in crystallography, you just multiply by integers as much as necessary in order to find integers. Now we have to define the crystal planes, okay? Again, crystal planes are expressed by means of triplets of integers. In this case, they are surrounded by round parentheses, or in some other case with parentheses with a tip, okay? Either this case or the other. We shall see both, okay? In this case, we have the round parentheses, okay? So how do you define the indices? Now, let's look at the right part of the figure, which is the easy one, okay? The gray area is a portion of a plane. And you see immediately that this plane has a property. It intersects the x-axis in the position 1 at the distance equal to 1 with respect to the origin. At the same time, it intersects the y-axis at the distance equal to 1 with respect to the origin, and the same in the z direction, okay? So this is just a starting point. We count the interceptions, or the intercepts, sorry, with the axis. We count the distance of the intercept with respect to the origin, okay? This intercept must be a node. So we simply count how many characteristic vectors we need to reach the intercept from the origin, okay? Now, assume that you rotate this triangle along this line, okay? So that this vertex goes up and intersects the z-axis at a position equal to 2, okay? Obviously, the indices will be 1, 1, 2, because the index on the x and y axis did not change, and the other one has gone upwards, okay? Continue rotating, you may reach position 3 in the vertical direction, so you reach 1, 1, 3 as a description of the plane, okay? But there is a risk that if you rotate too much and this triangle becomes vertical, the intercept with the z-axis becomes infinite, okay? So crystallography does not love infinities, did not love non-integers, and does not love infinities either. So we must find a little bit more complicated construction in order to avoid at the same time both non-integers and infinities when we describe the crystal planes. So there is a formal construction that eventually leads to a triplet of integers that are called the Miller indices of the crystal plane. So let's consider that this crystal plane is called pi, okay? And this plane is identified, as we said before, by a triplet of integers m1, m2, m3, okay? Assume for a moment that they are finite, okay? You remember from geometry that if you multiply m1, m2, m3 by a number that is non-zero, you obtain another plane that is parallel to the original one, okay? So by changing this parameter R, you find a whole family of crystal planes, all parallel to each other, okay? So the first rule is we adapt this multiplying parameter R in such a way to obtain the minimum triplet. What we want is to obtain the triplet of integers describing the plane that is the minimum one, okay? This triplet corresponds to the plane of the family that is closest to the origin. How do we do it? Very simply, we find the largest divisor of M1, M2, and 3, we call it capital M, and then we divide the original triplet by capital M. So we obtain another triplet M1 prime, M2 prime, and 3 prime. This is defining a plane parallel to the original one and the closest to the origin, okay? We still have a risk, and the risk is that if it happens that this plane is parallel to one of the axes or two of them, one or two of the indices become infinite, okay? So in order to avoid this occurrence, instead of considering M prime 1, 2, and 3, we consider the inverse of M1, M2, M3. So if we have infinities, we get zeros instead, okay? But on the other hand, if one of the original numbers, one or two of the original numbers, M1 prime, M2 prime, and 3 prime, were not infinite, but finite, then the inverse is a non-integer, okay? And we don't like non-integer, okay? So the story is not finished yet. After taking the inverse here, we must multiply these numbers by a number in order to eliminate the fractional number. And of course, this number will be the least multiple, capital N, of the M prime. So in so doing, we eventually find a final triplet, M1 double prime, M2 double prime, etc., that are neither infinite nor fractional. They are just integers, 0 included. Okay? Let's take an example. Assume that the original numbers M1, M2, M3 are infinite 2 and 4. Okay? So first we divide by 2. So infinite stays infinite, 2 becomes 1, 4 becomes 2. So this is a plane that is parallel to the original one, but the closest to the origin. Then we take the inverse, so infinite becomes 0, 1 becomes 1, 2 becomes 1/2. So we have eliminated the infinity, but we now have a non-integer. We multiply by 2, and we get 0 to 1. Okay? For instance, if you play this game for these two planes in gray, the one that is parallel to the xy plane, okay? This crystal plane has the indices 0, 0, 1. And this one, parallel to the z and x axis, has the indices 0, 1, 0. Okay, and this is 1, 1, 1. Nothing changed. Okay, so now we have a general procedure suitable for describing nodes, crystal direction, and crystal planes. Now we have to investigate a more realistic type of crystal. The question is, how is silicon made? Okay. So we consider this example. It is not yet silicon, almost, okay? So this figure represents a type of cubic lattice that is called face-centered cubic lattice. Face-centered cubic. The short is FCC, face-centered cubic. What is the property of this FCC lattice? The property is that we have one atom at each vertex of the cube. And then we have additional atoms at the center of each face of the cube. If you think of silicon, okay, the colors of the atoms have no meaning. Okay, these atoms are all equal to each other. The colors are just there to better distinguish the atoms. Okay, so the atoms over the vertices, of course, are 8. This one gray, this white, this gray, this black, and the other 4 on top. And then we have 4 more atoms at the center of each face. So this black one is at the center of the right face, this gray is at the center of the left face, center of top face, center of bottom, front, and back. Okay, this is not yet silicon, almost, okay, almost. So this is a typical form of the face-centered lattice. Silicon is a face-centered cubic lattice with additional atoms with respect to those that you can see in this figure, and they are shown in the next figure. Consider for the moment the portion of the figure on the left, okay? And remember, silicon is a chemical species that belongs to the 4th column of the periodic table of the elements. What does it mean? It means that each atom of silicon has a number of electrons in it, okay? And of these electrons, 4 electrons are external, are in the external shell of the atom. There are also other electrons that are more inside, closer to the nucleus, okay? But those that are important for us are the 4 electrons that are in the external shell. Why? The reason is that these atoms are those that are able to form chemical bonds with other atoms, because the chemical bonds are formed by the electrons that are more external in each atom, okay? So, the silicon atom has 4 external electrons. That means that it is able to form 4 bonds. It is able to attach itself to other 4 atoms. In the case of a silicon crystal, the other atoms are again atoms of silicon. So in a perfect silicon crystal, each atom of silicon is attached to other 4 atoms of silicon. How do they place themselves in space? Of course, they try to place themselves in some symmetrical placement, okay? In order to have a symmetrical arrangement of the positions. So the symmetrical arrangement can be seen in the left part of the figure, in which you can see a cubic block. At the center of the cubic block, there is 1 silicon atom, and then there are 4 more silicon atoms in some vertices of the cube in symmetrical positions, okay? So the distances between each external silicon atom and the central silicon atom is the same for all, okay? When you have a cubic structure in which you have some atoms at the vertices and 1 other atoms in the center, okay, this structure is called body-centered cubic structure, okay, BCC. But if you look closely, you see that essentially the form of the positions of these atoms is that of a tetrahedron, okay? Obviously, when you consider the central atom of this arrangement, the central atom has formed 4 bonds. So the possible bonds of this atom are completely saturated. 4 external electrons, 4 bonds. But the other atoms on the vertices have, for the moment, used only one external electron, 1 bond. So they are able to continue to attach themselves to other silicon atoms, okay? So if the external atoms of the small cube attach themselves to other silicon atoms, you start forming structures like those that you can see in the right part of the figure, okay? So let's start with the bottom case, okay? You have 2 cubes, and these 2 cubes are connected because this atom that I'm showing with the mouse is connected at the same time with the center atom of the left cube and the center atom of the right cube, okay? The white dot here and the white dot here are also silicon atoms, but they do not belong to these 2 cubes, okay? They belong to other cubes of the lattice. Similarly, if you take the upper part, you have the same structure as in the lower part. It is simply rotated by 90 degrees over a vertical axis. You see, it's just the same structure but rotated. Okay? Now, assume that you put these two structures together. So you lower the two cubes on top in order to put them exactly over the two cubes at the bottom. Okay? We shall see the result in the next figure, but before we continue, observe that the length of the side of the small cube is called a half. So of course, the length of the side of the new cube that we are going to obtain after putting all these things together will be a. Okay, because we are putting two cubes, one near the other. This a is what is called the lattice constant, and it is the period of the silicon crystal. And of course, since it is of a cubic structure, this period is equal along the first, second, and third directions of space. Okay, so we go now to the next figure. It is just the same, simply the two blocks that you can see separated here, they are put together in the next figure. Okay. So you obtain this type of structure. Okay. Again, the white dots are silicon atoms, but they do not belong to this structure. They belong to the structure that is on the right or on the left or below, and you can imagine that this structure will repeat itself periodically in the three directions of space. Okay, so indeed it is a cubic, face-centered cubic crystal. Okay, the vertices of this cube are this black, this white, this black, this white, this black, this white, this black, and this white here. The atoms at the center of the faces are this one, right, left, front, back, top, and bottom. And then we have four additional atoms that are the centers of the original small cubes. This one, this gray, this gray, and this gray. Okay. The lattice constant is the side of the cube, and we call it A. Okay. Silicon and germanium have this structure. So a pure crystal of silicon has this structure with a lattice constant that is indicated here. For silicon, the lattice constant is 5.43 angstrom. And the lattice constant for germanium is 5.64, almost the same, almost. This is the reason why we can make compounds, not compounds, we can process technologically layers of silicon and put layers of germanium on top, because the distances between the atoms are almost the same. So with the little deformation, the atoms of germanium and silicon adapt and connect with each other. Okay, this is so because the distances, the lattice constants are so similar. Okay. We stop here for 10 minutes because it is 4:30 and we shall resume at 4:40. Okay. If there are questions, you may ask them now. So we continue. And you remember we were observing the length of the lattice constant in silicon and germanium. When we consider the units, okay, you remember there are units that are politically correct, and they are the units that go by 1000, a factor 1000. So when you start from the meter, you divide by 1000, you have the millimeter. Then you divide by 1000 again, you have the micrometer or micron. And then you divide again by 1000 and you obtain the nanometer. Okay. So the nanometer is a meter multiplied by 10 to the minus 9. 1 angstrom, as you remember, is 1/10 of a nanometer. So 1 angstrom is a meter divided by 10 to the 10th power. So in principle, the angstrom is not politically correct. It should not be used, okay? But it is so convenient because the size of an atom is typically about 1 angstrom, okay? So the angstrom is a reasonable unit, although it is not politically correct for describing properties like size of an atom or distances among atoms in a solid and so on. By the way, the lattice constant is not the minimum distance among atoms in the crystal, okay? Of course, the minimum distance is the distance between the center and the vertices of the original small block of tetrahedral form that we started from, okay? It is very easy to find that this minimum distance that is called d in the figure is equal to the lattice constant by the square root of 3 divided by 4. Okay. Another interesting thing is that you see the lattice constant of silicon in angstrom is 5.43 and that of germanium is 5.64. So these figures show that it is possible to measure distances up to 2 figures in angstrom. That means 10 to the minus 12 meters, which is very small. Okay. We do by optical measurements. We exploit properties of monochromatic light, okay, and from the interference of light with the crystal, we can measure some properties of the crystal, including these distances. Okay, so this is it for the structure of crystalline silicon and crystalline germanium. This structure goes under the general name of diamond structure. It is called diamond structure because also carbon in the diamond form has the same structure. Okay, you remember that carbon may have two forms, two crystalline forms. One is this one, and the other one is graphene, okay, hexagonal. Okay, so when carbon is in this form, it is called diamond. Diamond is not used in the technology because diamond is an insulator, it's not a semiconductor. Okay, but the structure is the same. Then there are other materials that are compound materials, so they are made of two chemical species combined together that also have a structure very similar to this. And there are several possible combinations of two different chemical species that combine together to provide a structure similar to that of diamond. And these chemical species, for instance, are gallium, Ga here, and arsenic, As, okay? Gallium belongs to the third column of the periodic table of elements, and arsenic belongs to the fifth column, okay? So for this reason, a compound like this one that is called gallium arsenide is also called a 3,5,3,5 structure because one of the two elements belongs to the third column and the other one to the fifth, okay? There are many possible combinations. You see there is gallium arsenide, gallium phosphide, so with phosphorus, gallium antimonide, Sb is antimony. Then we have indium arsenide, indium phosphide, indium antimonide, and finally aluminum antimonide. All these are possible 3,5 compounds that form a structure similar to diamond, and this structure is a semiconductor. Okay? And again, you see that the interatomic distances, sorry, the lattice constants are in the range of 5 to 6 angstrom. Okay? So this is an example, okay? Here the atoms have a different size. The size has no meaning, just to make them distinguishable from each other. For historical reasons, this structure is not called diamond. It is called the zinc blende structure. You can see here written at the bottom. Now we have a question. If we start from a cubic cell, let's take the simple one, okay? Let's start with a cubic cell, and then let's try to construct, you remember, the Wigner and Zeiss cell of this lattice. What do we obtain? It is not so obvious. Okay, it is not so obvious. What we should do is, you remember, we take an atom, we connect the atom with one of the neighboring atoms, and then in 2 dimensions, we take the axis, that is the segment normal to the segment connecting the 2 atoms and crossing the center. Okay. When we go from 2 dimensions to 3 dimensions, of course, instead of taking the axis, we take the plane that is normal to the segment connecting 2 atoms at the center of the segment itself. Okay. In this way, we form the Wigner and Zeiss cell of the lattice in 3 dimensions. We can do it also, as you remember, for the scaled reciprocal lattice. And in particular, you remember that the Wigner and Zeiss cell of the reciprocal scaled lattice centered in the origin is called the first Brillouin zone. So what is the form of the first Brillouin zone for a cubic lattice like that of silicon? The form is like this. You remember that in the reciprocal scaled lattice, the vectors are called K. So they have 3 components that are K1, K2, and K3. They should be small letters. They are indicated here as capital letters, but it is the same. So K1, K2, and K3 are the coordinate axes, okay? It happens that in the cubic lattice, the direction K1 coincides with the crystal direction that we called 1, 0, 0. K2 corresponds to 0, 1, 0. And K3 corresponds to 0, 0, 1. Okay, this is for the cubic lattice. Okay. So how is the Brillouin zone made? Of course, it is a volume. This volume has faces, and there are 6 faces that are squares. You see there are 3 squares visible in the figure, of which the center is indicated with X. And of course, there are other 3 faces that are also square, invisible on the other side of the volume, okay? So, the origin, for historical reasons, the origin in the reciprocal scale lattice is called the gamma point. So you see the origin is indicated with the capital gamma letter. The centers of the square faces of the Brillouin zone are indicated with the X letter. So there are 6 of them, 3 are visible in the figure. So if you go from gamma along the K1 direction, 1, 0, 0, you intersect the Brillouin zone in one of the X points. The same if you go along the K2 or 010 direction, and the same if you go into the 001 direction, that is K3. And then there are 8 faces of the volume that are hexagons. You can see 4 of them here, 2, 3, and 4. And the center of each hexagon is called L, capital L. So it is the L point. So there is a total of 8 L points at the boundary of the Brillouin zone for the cubic lattice. Okay. If you connect the gamma point with this L point, you are going in along the 111 direction. So it is intuitive that there exist 8 possible directions in which the indices are 111, because you have 111 and the opposite on the other side would be -1, -1, -1. This one here would be some combination of +1 and -1. So you have 8 combinations of directions in which the indices are either 1 or -1. Why is the Brillouin zone so important? The Brillouin zone is important because it is the interval of periodicity of the reciprocal scaled lattice. So we have a sort of duality here with respect to the direct lattice. You remember, we started a reasoning saying if the structure is periodic, we expect that its physical properties should be periodic. So we describe them by periodic function, and then we take the Fourier transform, or we make a Fourier expansion of these functions. When we do the Fourier expansion, we go into the reciprocal scale space, and this is also periodic. So we also find some other properties that we shall see that are periodic. So we shall find a periodicity of some properties in the scaled reciprocal lattice. Obviously, if you know that a function is periodic, it is sufficient that you investigate the properties of this function only in one period. It would be completely useless to go outside a period because you find the same thing because of periodicity. Okay? So many properties that we shall see in a crystal will be investigated inside the first Brillouin zone because it is an important interval of periodicity of the structure. Now we have to change the slides because I need to show you Okay, for a while I'm going to use these notes. These notes are uploaded in the Virtuale website. Of course, they are much longer than the part that we're going to use. There is a little part of analytical mechanics. I just wanted to remind you that if you consider a particle or a system of particles, for simplicity, consider a Cartesian set of coordinates, okay? And these particles are subjected to external forces and also they interact with each other, okay? We have the important case in which the forces acting on the particles are conservative. You remember the meaning of conservative is this, that there exists a function V that we call potential energy. This function is a scalar function that depends only on the coordinates. And it has the property that if you take the derivative of this function with respect to any coordinate, okay, you find a component of the force that acts on the particle along that component, okay? And if you have many particles, you can do the same, okay? The definition can be extended also to systems made of many particles, but in our case, we need only to consider a single particle, okay? If you have a conservative force, then oops. Okay, if you have a conservative force, then you have the conservation of the total energy. This is elementary physics. You remember, you define the kinetic energy of the particles. Here it is called T. And it is 1/2 the mass times the square of the velocity. In a conservative case, when you add T and V, although separately T depends on time because the velocity of the particle depends on time in general. And V also depends on time because V depends on the position of the particle and the particle the position of the particle also depends on time because the particle is moving. So independently from each other, separately from each other, T and V depend on time. But in a conservative case, the sum is a constant. It is called the total energy. And this total energy is independent of time, okay, in the conservative case. Another issue is that for the conservative case, you can define the momentum of the particle, you see it here, simply as the product of the mass times the velocity. So if you are in a one-dimensional situation, the velocity is x dot, okay? remember, for this result to hold, P equal to M x dot, you need to be in a conservative case and use the Cartesian coordinates, okay? If you consider a non-conservative situation like that, when the particle is subjected to the action of the electromagnetic field, the momentum is not equal to the mass times the velocity. It is different from that, okay? In this case, it is equal to the product of the mass times the velocity. So the kinetic energy, instead of being written as 1/2 mass times the square of velocity, the kinetic energy can also be written as the square of momentum, p squared, divided by 2m. So this is a one-dimensional situation. This function h is called the Hamiltonian function, okay? This is definition of the Hamiltonian function in this case. As I said before, P separately depends on time, X and also V separately depend on time. This sum does not depend on time because the total energy is conserved, okay? When we have a one-dimensional situation, we can do some graphics. It is relatively easy to do some graphics to represent these functions graphically. Obviously, the kinetic energy is always a parabola, because if you represent the kinetic energy as a function of P, you have a parabola. The potential energy is some function. I mean, it may be a complicated function, okay? When we consider a crystal, we must consider the potential energy acting on one of the electrons that are inside the crystal, okay? The crystal has many electrons in it, okay? Those that belong to the external shells of the atoms can move relatively easily. Those that are more in the interior of the atom don't move that much. They are attached to the atoms. Okay, so we consider as usual only the external electrons. We take one of these electrons and we try to represent the type of potential energy to which the electron is subjected. It is intuitive that this potential energy must be periodic, because the crystal is periodic and we anticipated that the physical properties of the crystal are periodic. Okay, so there will be a figure somewhere here. The figure on the right represents a possible type of periodic energy, completely unrealistic, of course, okay? But for the moment, let's consider the figure on the left, okay? The figure on the left is a diagram in which we consider a very, very simple case. The simple case is that of a particle, the simple case of a free particle, a particle that is not subjected to any force, to any external force, okay? What does it mean? It means that, you remember, the force is minus the derivative of the potential energy. If there is no force in this example, that means that the derivative of the potential energy must be equal to 0. So the potential energy is equal to any constant, okay? So assume that the potential energy is equal to some constant that we call V0, okay? And then we express the potential energy, the kinetic energy, and the total energy in a diagram in which on the horizontal side we express momentum. You see in the left part, in the left figure, we have P here as abscissa. And sorry. In the vertical axis, we have the energies, okay? So we must represent a function that is a parabola plus a constant. So, of course, the constant is arbitrarily set equal to 2, is equal to 0.3. You read it on the left axis. And the parabola is the blue line. So, the blue line is the total energy. Is V0 plus P squared over 2m. Okay? Now, consider, for instance, the situation in which the particle has an energy equal to the green dot number 1. Okay? What does it mean? It means that momentum is different from 0. Okay? So this particle is moving because the momentum is non-zero. Okay? So this particle is moving. The total energy is the distance from the green dot to the horizontal axis. The total energy is made of the sum of the potential energy, that is the orange or red line, horizontal, plus the kinetic energy, that is the green vertical line. Okay? Remember, if a particle is subjected to no force, the velocity of the particle does not change. So the green dot represents the dynamics of the particle forever, or at least as long as the particle will not be subjected to some external perturbation that will change its motion. Case number 2 is that of a particle whose momentum is 0, which means also that the velocity of the particle is 0. So situation number 2 represents a particle that does not move. Okay. Situation 3 prime represents the situation of a particle that has some momentum that is positive. Okay. If the particle is left unperturbed, the momentum does not change because the velocity cannot change. Okay. So again, if the particle has initially a dynamic situation corresponding to case 3 prime, the particle will always stay in that position in this diagram, so the momentum will never change. Now, assume that at some point there is an external perturbation that acts on the particle and changes the motion. Okay, like you are a spectator, you see the particle that is coming near you, you kick the particle, okay, and increase the velocity of the particle because you perturb the motion, okay. So what happens in this diagram? Well, if you kick the particle in a way that increases the velocity, so it makes the velocity more positive, you expect that P will go to the right. So the particle will be represented after the perturbation instead of point 3 prime by point 3 with 2 primes. Okay. So remember, this looks simple, but you must remember that this is a diagram for a very, very simple situation in which the potential energy is a constant and the diagram has momentum in the abscissa. Okay. Now we go to the next figure in which we consider a completely different situation. The particle is subjected to forces, and these forces derive from a periodic potential energy. So the diagram will not have any more P in the abscissa, it will have position. It will be different, okay? So in this diagram we have, let me try to make it a little bit smaller. Okay. Okay, so the black line is a periodic potential energy, periodic in space. Looked at along the horizontal axis, we have X. It is a one-dimensional situation in which we have a periodic potential energy. Since we have a potential energy, again, the motion of the particle is conservative. That means that the total energy is independent of time. It is conserved in time, okay? It's some constant. Now, we have two possibilities in this case, because you see that the curve the black curve representing the potential energy has minima and maxima, okay? So we have one possibility that is represented by the green line, in which the constant representing the total energy is larger than the maximum potential energy, okay? What does it mean? It means that, you remember, the total energy is kinetic plus potential energy. If the total energy is always strictly larger than the maximum potential energy, then the kinetic energy will always be strictly positive, never equal to zero. Okay? If the kinetic energy is always strictly positive, then the velocity will be always non-zero. Okay? So this particle will always move, and we shall see it in a minute. It will always move in the same direction, either always to the right or always to the left. Who decides whether the particle moves to the right or to the left? It is decided by the initial conditions, okay? The motion of a particle, you remember, is described by a second order equation in time. So we need two initial conditions, one for position and one for velocity. If the velocity is initially positive, and we are considering the situation with the green line, then the velocity will always be positive, because it can never become equal to zero, because the kinetic energy in this case can never become zero, okay? So the velocity can never become zero. If it starts positive, it will be always positive. A second possibility, which is not shown here in the figure, is that the total energy is smaller than the minima, the absolute minima of the potential energy, okay? This case is physically impossible, at least in classical mechanics. Why? Because if the total energy is always, that means at any position, smaller than the potential energy, that means that the kinetic energy is negative. But this is physically impossible because the kinetic energy is proportional to the mass, and the mass is positive, and to the square of the velocity. So the square of the velocity can never be negative. Okay? So the case in which the total energy is smaller than the absolute minimum of the potential energy is physically impossible and is not to be considered. And then we have the intermediate case that is represented by the blue line. That is, the total energy has a value that is intermediate between the absolute maxima and the absolute minima of the potential energy. So what happens in this case? In this case, you see there is a segment marked by the two red dots, okay? So assume that the initial conditions of the motion are such that the particle is in that segment. Okay, so it is between the two red dots, and at time equal to 0 is going to the right. Okay, so as long as the particle is inside the segment, the total energy is larger than the potential energy. So the kinetic energy is non-zero, so the particle keeps moving. And by assumption, it is moving to the right, okay? At some point, the particle will reach the red dot on the right. At the red dot on the right, in this position, the total energy intersects the potential energy, which means that at that point, the kinetic energy becomes equal to 0. The particle cannot proceed to the right, because if the particle proceeds to the right, then the total energy becomes smaller than the potential energy, and the kinetic energy becomes negative, which is impossible. So the only possibility for the particle, when it reaches the red dot on the right, is that the particle bounces back and goes to the left. So we have an inversion of the motion. Then the particle will proceed to the left. It will reach the other red dot on the left, and again it will bounce back. Okay, so if the total energy is the blue line, the particle can stay only in one of the two intervals, one that is marked by the two red dots. Which interval? Well, the interval of the initial condition. If x initially is such that the particle is inside that interval, it will stay forever in that interval and it will oscillate forever, right to left, left to right, right to left. Okay, so the motion will be oscillatory. Okay, these are the only two possibilities in classical mechanics. In classical mechanics, we have only these possibilities. Okay. Now we are almost at the end of the second hour. The point is, assume that you want to describe the motion of a particle inside the crystal, that is inside the periodic energy, using for the moment classical mechanics. It is a very difficult task because the form of the potential energy to which the particle is subjected is very complicated. Okay. Now, let's take the case of the green line, that is the easy one, okay, in which the particle keeps moving always to the right or always to the left, depending on the initial condition. We don't consider the case of the oscillations, okay? What do you expect of the motion of the particle whose total energy is the green line? Well, consider the situation when the particle is in this position marked by the mouse, okay? So you see, it's on top of a maximum of the potential energy, okay? So if the potential energy is a maximum, the kinetic energy is a minimum because the total is the green line, okay? So here the particle is slow. Then if the particle moves to the right, the kinetic energy will increase because the distance between the green line and the black line is increasing, okay? When we arrive here, the distance between the green and the black line is very large, so the velocity here will be very large, but then when the particle reaches this point, the velocity will again small and exactly equal to the velocity here, okay? So intuitively, we see that the velocity changes periodically. Small, larger, 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 and then small again. And then again, large and large and large, small again, okay? So we don't have an oscillation like in the blue line, but we have some sort of periodicity of the motion. Slow, not so slow, slow again, etc., okay? Now, the reasoning is this. What is the typical period of the potential energy in a crystal? The period is determined by the distances of the atoms. So the typical period is the lattice constant, like 5 angstrom, you remember, okay? And the question is, do we really need to consider the details of the motion of one electron over a distance of 5 angstroms? Probably not. It would be a waste of time and efforts to describe the details of the motion of the electron over one period of the potential energy. Of no use, okay? There is no use in that, okay? So the idea is, why don't we take the average? Why don't we calculate, instead of the velocity or the momentum at each position, why don't we take the average velocity or momentum of the electron over a period of the lattice. More or less, we obtain enough information from the average velocity. So this is a concept that is very important, okay? We shall do some calculation. We shall limit ourselves to classical mechanics. We don't do it with quantum mechanics, okay? But the concept is very important. What we try to do is we consider the average motion of the electron in a periodic potential, and we shall find very, very interesting conclusions. So we stop for 10 minutes and we shall resume at 5:40. As I said before, we consider the possibility of using, instead of the actual velocity or momentum of the particle, we take the average over a period. The period is indicated with the small a in the notes, so you can see it here. We have the potential energy at x plus a is equal to the potential energy at x for any x, because a is the period, okay? And then we consider the green line so that the total energy E is strictly larger than the maxima actually of the potential energy. You remember the kinetic energy is T, mass times the square of velocity divided by 2. This is also strictly positive, never vanishes, okay? We assume that the particle has an initial velocity oriented from left to right, so the particle always goes to the right, okay? And then it is very easy to integrate the equation of motion in this case, because if the kinetic energy plus the potential energy is equal to the total energy, we can rearrange the expression, okay? This is the kinetic energy divided by 2 over m, will be equal to E minus V, okay? And V is some function of x that is prescribed. So the function V of x is known, okay? Then we take the square root. So we can express the velocity as a function of position. And the difference E minus V in the square root is always strictly positive, okay? You see, this equation is separable because we can express dot x as dx over dt, then we bring dt to the right, we bring this quantity to the denominator on the left, and after the separation we have this, okay? So we express the differential of time as a function of position, okay? And then we integrate over a period, okay? So when we integrate over the period, the integral of dt gives you the time tau necessary for the particle to move over one period, okay? Then we have the square root, that is a constant, and then we integrate over the period. When we integrate over the period, we must select, sorry, an initial position for the integral, call it S. S is some arbitrary initial position. And of course, since we are integrating over a period, the other extremum of the integral will be S plus A plus the period, okay? So when you calculate this integral, you find immediately that this integral does not depend on S. Okay, it's completely independent of S because V is periodic. Okay, so it's easily calculated. You take the derivative of tau with respect to S and you find 0. Okay, so that means that the time that is necessary for the particle to cross a period of the potential energy does not depend on the initial position of the particle. Okay, it's some time that is, in principle, one can calculate. Okay. Then we can do some other average. Okay. We may say, why don't we calculate the average momentum of the particle over a period? Okay, so the actual momentum of the particle is small p, okay? Of course, small p depends on time, because you remember the particle accelerates and then decelerates and accelerates again, okay? So the velocity of the particle depends on time, and the momentum, that is the mass times the velocity, also depends on time. So small p is a function of time. What about the average? Let's see. We can calculate the average very simply because you remember momentum is proportional to velocity, okay? So it is mass times velocity. And velocity was expressed a minute ago. Velocity was expressed as a function of position in equation 22. Okay, so if you multiply by the mass here and there, you have momentum as a function of position. Okay, so then you integrate momentum again over a period. And since you want to obtain the average, you integrate over a period and then you divide by a period in order to obtain the average proper of this function, okay? So the average is called capital P. This is the average momentum, okay? Again, you see very interesting things that, number one, average momentum does not depend on the initial position S of the integral for the same reason as before, okay? But also you see that when you integrate with respect to X, you saturate X, okay? So, of course, P will depend on the form of the potential energy V. But when you conclude this integration, there will be just one parameter important in the definition of P, that is the total energy. Of course, there will be also the mass, the period A, that is a geometrical parameter, but the fundamental parameter on which the average momentum depends is energy, okay? But you remember, energy is a constant of motion. So energy does not depend on time. It follows that the average momentum is a constant of motion as well. So that is, does not depend on time. So this is fundamental. The actual momentum, small p, depends on time. The average momentum does not depend on time, okay? So if you consider the average momentum is like having a free particle, because you remember for a free particle, momentum is a constant. This is not a free particle because it is subjected to the potential energy, so it is not free. But if you take the average momentum, you obtain a constant of motion, okay? And since you are interested not in the small details of the motion, but you are interested in the motion in the average, well, if you use average momentum, you have a constant of motion. It is like recovering a free particle because you are hiding the details of the microscopic details of the potential energy in this operation of averaging that you are doing, okay? Another important thing is that when you take the relation between velocity and this expression, you take the square root, okay? When you take the square root, you have a double sign, okay? So, in principle, to the same value of energy, there are actually two possible velocities, one positive and one negative. That means that there are two possible momenta, one positive and one negative, and also two average momenta. So that means that two opposite values of the average momentum correspond to the same energy. And that means that energy is even with respect to momentum. Okay? So, substantially, we have found a very important result that if we consider the average momentum, we find a constant of motion, like in the case of a free particle. Momentum is related to energy only. Energy is even with respect to not only momentum, but also the average momentum. Okay. The only thing that actually changes is that the relation between the average momentum and energy is not quadratic anymore, because there is this complicated relation in which you have this expression under the square root and you perform an integral, okay? So you have to pay a price when you use average momentum instead of momentum. And the price is the relation between energy and momentum is not quadratic anymore. It may become more complicated, okay? But we can survive to this, okay? Is all of this useful? It is useful, but it looks very limited because the only possible application until now is to the case of a periodic potential energy. When we consider a semiconductor device, you have a crystal. The crystal is actually periodic, so this reasoning applies to that. But the device has contacts, and you also apply voltages to the contacts. So the issue is that when you apply the voltages, the potential energy that acts on the electrons inside the crystal is not anymore the periodic energy only. It is the superposition of the periodic energy imposed by the crystal plus the external periodic energy, the external non-periodic energy imposed by the generators, by the voltages that are applied to the contacts. Okay, so in some sense we destroy the nice calculation that we have done, because instead of a periodic potential energy, we have another potential energy that is the sum of one periodic and the other non-periodic. Okay. However, we can still consider the average momentum. Why? Because the total energy, the total potential energy that exists in a crystal when we apply external voltages to the contacts is made of two contributions. One is the periodic energy of the atoms, and that is a very, very strong and rapidly varying function. Okay, you remember it is a function whose period is of the same order as the lattice constant. Okay, so the periodic potential energy changes very much in a very short distance. That means that the forces due to that are enormous. The additional forces imposed by the external voltages applied to a device are actually very small. They are non-periodic, but very small. Okay. So we can try to continue on the same line as before by assuming that the external forces can be considered as small perturbations to the existing periodic potential energy due to the atoms. Okay, and you can see this in the figure. Okay. Consider the black line that is the original purely periodic potential energy. Okay. Still consider the case of the green line. So the total energy, we can still define the total energy because all forces are conservative. So we have a total energy, and this total energy is a constant of motion. Okay. And then we assume that we superimpose to the periodic potential energy a small non-periodic perturbation. You see it is written in the green, in the caption of the green line. It is the original potential energy V of x that is periodic plus some constant times x. Okay. Of course, the additional force produced by this c times x is the derivative with a minus, so it is minus a constant. Okay, so it is like we are adding a constant force due to a linear potential energy. Okay, so we consider that as a small perturbation, and then we shall try to repeat the calculation that we had before by calculating again the average momentum, okay, incorporating into the calculation also the small perturbation. Okay, let's see what happens. So the small perturbation that in the figure was called Cx, here more generally is called delta V. Okay, delta V is small with respect to V, and also delta V has a weak dependence on x, whereas V of x has a strong dependence on x. Okay, so the dependence of delta V on position is so small that we can consider it as almost constant over several periods of the crystal. Okay, And then we just recalculate the integrals that we had above, okay? But in order to distinguish the case of a really periodic potential energy, where we calculated tau and capital P, here we use different symbols, okay? So we call the average period tau with a tilde, and the average momentum is capital P with a tilde on it, okay? And since delta V is not periodic anymore, these integrals depend on position S, okay? From now on, it is pure mathematics, okay? So let's approximate the square root of E minus V minus delta V, okay? You remember the approximation of the square root to first order is this. So the right-hand side of equation 29 is the perturbation, is the Taylor expansion to first order of this square root when delta V is much smaller in modulus than E minus V, okay, which can we can always assume, okay? So this is approximation number one, a Taylor expansion inside the integral. Number two, you remember we said delta V varies very little with respect to position, so we can consider it almost constant over a period, okay? If it is almost constant over a period, here you see delta V, we replace delta V of X with delta V of S, okay? S is the position where we start calculating the integral, okay? Then what we do is we replace the simplifications in the integral. At that point we can calculate the integral. And we can calculate the integral very easily. What we find is that the actual momentum P tilde is the momentum P of the unperturbed situation, which is a constant of motion, as you remember, minus tau over A times delta V of S. You remember tau is the time necessary for the particle to cross one period in the unperturbed situation, okay? Now we do another little calculation, okay? You see we have formula number 30. We recalculate formula number 30, replacing S with S plus A, here and here. And then we subtract, okay? You obtain 31. And this is the fundamental result. It tells you that the variation of the average momentum in time, that is the variation of P minus the original P divided by the time necessary for the particle to cross one period. So the variation of momentum, you remember in mechanics, the variation of momentum with respect to time is the force, is equal to minus the variation of the external potential energy divided by the period, okay? It's like the derivative of delta V with respect to X, okay? So this is a fundamental relation. It tells you that In this type of approximation, in which the external force is much weaker than the periodic force, and also the external force changes little over a period, okay, you can eventually find that the change in the average momentum is due only to the external perturbation delta V. The change in momentum is the force. So it is like, in the average, the only force acting on the particle is the external force. This is a very fundamental result. Why? Because it gives you the possibility to describe the dynamics of a particle inside the crystal by considering only the external forces. You embed the potential and the periodic potential energy of momentum in the average operation that you carry out on momentum. Okay? So this is the fundamental ideas are average momentum instead of real momentum. External forces instead of the total forces acting on the particle, provided the external forces are almost constant over a period and not too strong, which is the case for the typical operating conditions of semiconductor device. If you understand the reasoning, you can also appreciate the fact that the outcome of this reasoning is enormously useful. Essentially, when we use average momentum in a crystal or in a periodic structure, it's like we are considering free space, particle in a free space with some external force. It's like the crystal has disappeared, okay? You may say this is too much. We cannot just make the crystal to disappear. Actually, there is one thing that is left of the crystal. You remember when we calculated integral 24, okay, you remember we said the relation between energy and average momentum will not be quadratic anymore, because it is much more complicated due to the integral and the other quantities that you see here, okay? So this is the price we have to pay. We eliminate the action of the lattice that acts on the particle with the periodic potential energy, but this action comes back in some sense because the relation between energy and average momentum will not be quadratic anymore. It will be a much more complicated relation, but this is a price that we accept to pay, okay? What are the limits of this analysis? There is essentially one limit, that this analysis is done using classical mechanics, okay? However, when we consider microscopic particles, we cannot use, well, we can use classical mechanics, but it is insufficient, okay? We must use quantum mechanics, okay? So we have no possibility to do that because we don't have the fundamental of quantum mechanics, at least for the moment, okay? So I shall give you the results that one obtains by repeating somehow the reasoning that we have been carrying out so far, adding also the quantum mechanical treatment to the dynamics of the particle. Okay. I think we don't need any more this part of the material, so we go back the other one. There are several differences in the results that we obtain using quantum mechanics over the crystal with respect to the case of a treatment based on classical mechanics. And I will tell you the most important ones. We shall still be using average momentum. This average is not to be considered in time, is a statistical average. And one can demonstrate that when we use quantum mechanics, the average momentum of a particle in a crystal is proportional to the vector belonging to the scaled reciprocal lattice that we call K. So that vector that until now had only a geometrical meaning. It was a vector that was useful for defining some properties of the scaled reciprocal lattice. That vector has also a physical meaning. It is proportional to the average momentum of the electron in the quantum mechanical treatment of the particle. Because of that, then we expect, you remember, energy, when we take the averages, energy depends on the average momentum. That means that energy is expected to depend on K. Okay, so the relation E as energy as a function of P of classical mechanics is replaced by a relation E as a function of K in quantum mechanics. One could also use the symbol P in the quantum mechanical case. It is not forbidden, but it is customary to use K. Okay, so E of K is the relation between energy and momentum that comes about in quantum mechanics. You already expect that this relation is not quadratic. Okay, this relation is not quadratic. This is not the only difference. You remember that when we considered the scaled reciprocal lattice, we also observed that we have a periodicity also in that space. Okay, so one of the outcomes of the quantum mechanical treatment that eventually gives you the form of the relation between energy and momentum, that is E as a function of K, shows you that this relation is periodic. So energy is a periodic function of momentum. Very different from a quadratic relation like the one that you obtain in classical mechanics. But you remember, when you have a periodic function, it is sufficient to consider only one period. And one period is, as you remember, the Brillouin zone. So from now on, when we have to consider the relation between energy and momentum, we shall consider that relation only in one period that is inside the Brillouin zone, okay? You remember the symbols, the origin is called the gamma point. If we go along the 100 direction, you go to the X point, right and left, okay, and that is the 2 points where the Brillouin zone has the boundary. So you stay between these 2 points if you want to consider, for instance, the direction 100, okay. This looks strange, but is one of the outcomes of the quantum mechanical treatment. We are indeed able to derive the relation between energy, total energy, and average momentum, also in the quantum mechanical case, and in a crystal it turns out to be periodic. One last difference between the classical case and the quantum case, and this is also looks rather strange, is that the relation between energy and K, or energy and average momentum, is a many-valued function. Okay, so to each K, there correspond many possible energies. Okay, so we find a function that is made of several, or actually infinite, branches. Okay, and we shall consider one branch at a time. Okay, this is not easy to digest. Okay, it takes time, but unfortunately there is no possibility to develop in full the quantum treatment of this aspect in this class. So in the next slide, I'm going to show you two of the possible branches of the E of K relation in the case of silicon, that of course is the most important semiconductor. First of all, you remember, even if you consider one branch at a time, this function depends on a vector. K has 3 components, K1, K2, K3. So it is impossible to represent graphically such a function anyhow, even if you consider one branch at a time. So the standard method to show the function is to select one specific direction in space. You remember that in a cubic lattice, the K1 component is aligned with the 100 direction, K2 with the 010, K3 with the 001, okay? So we simply consider the 100 direction and we show a part of the function. So we show the total energy that is in the vertical direction with respect to K1. Okay, this is one of the possible. Okay. what is this rectangle? Okay. On the vertical axis, we have total energy because we want to express energy as a function of the average momentum, so E of K. Okay. On the horizontal axis, we have the K1 component of K. The origin is the gamma point, because we must consider only one interval of periodicity in the reciprocal scaled lattice. And since we are in the 1, 0, 0 direction, you remember at some point this axis hits the boundary of the Brillouin zone in the X point. So the right limit here and also the left limit here are two of the possible X points. The total is 6, you remember, of the Brillouin zone. So the horizontal segment of the K vector is the portion of the axis that is limited to the Brillouin zone. So we are in the Brillouin zone, okay? And then we have many branches. So this curve that I'm following with the mouse is one of the possible branches of the multi-valued E of K function, okay? If you go outside of the Brillouin zone, this curve will repeat itself periodically, okay? So it will go down and then up, etc., periodically, left and right. The lower curve is another possible branch. It is not shown completely because this branch sooner or later should touch the position of the X point on the left and also on the right, okay? It is simply not shown, okay? Later on, or maybe next time, I'm going to show you other figures that are related to the same issue, okay? And also this branch repeats itself periodically, okay, to the left and to the right of the Brillouin zone. The question is, how many branches are there, okay? If you go to lower energies, not shown here, okay, you find some other number of branches and then they finish, okay? So there is a finite number of branches not shown here that are below these two branches, okay? If you go up in energy, there are infinite branches, okay? So there is no limit in the number of branches that are above these two branches. Below, there is a finite number. Above, there is an infinite number, okay? Another issue is that since the branches are periodic, of course, they must have absolute maxima and absolute minima. So the lower branch has, as you can see, an absolute maximum, and its value is called EV here, okay? The upper branch of the figure has two absolute minima. The name is EC. This is in one direction, but then there is also direction K2 and direction K3. And the upper branch has two more minima in the direction K2 and two more minima in the direction K3. So the total of minima of this branch is 6. Okay. You can also notice that EC is strictly larger than EV. So there is an interval of energies, that is the difference between EC and EV, that is called energy gap. And the symbol for the energy gap is E, as you can see in the figure, okay? Inside the energy gap, there is no branch, no energy curve, which means that it is impossible for the electrons to have energies in the gap, because there are no possible curves available for the electrons, okay? These curves represent the possible energies of the electrons as a function of the average momentum K, okay? So if there is no curve, like there is no curve in the gap, the electrons can never have energies in the gap, of values of energies in the gap. Continue drawing the branches, there will be another gap on top of the upper branch, then there will be another branch, another gap, etc. So actually, the structure of these curves is an alternation of branches and gaps, okay? Now, consider again the upper branch. You see the lowest energy of it is EC, okay? The highest energy is this maximum in the origin, okay? So the possible energies of this branch go from EC to a maximum, okay? So there is an interval of energies that is covered by this branch, okay? This interval of energy is called band. Band of energy is the interval of energies going from EC to the maximum. Again, if we consider the lower branch, we have a maximum that is visible, EV, and then there is somewhere a minimum that is not shown. So also in this case, we have a band. This band also consists of energy that are accessible to the electrons because there is a branch, okay? So in conclusion, the quantum mechanical treatment of the relation between energy and momentum provides an alternation of bands that are also called allowed bands because electrons can have energies in the bands, an alternation with forbidden bands, okay? This structure repeats periodically with respect to K, okay? So this is a much more complicated and of course non-quadratic relation that we find when we calculate the relation between energy and average momentum using quantum mechanics, okay? In principle, sorry, this relation applies to all electrons of the crystal, okay? So all the energies described by these curves are accessible to any electron of the crystal, okay? Which is somehow dangerous because one may think that then in order to describe the dynamics of the electrons, we should describe infinite bands, okay? Which is not very convenient, okay? Because actually there are infinite bands, okay? Fortunately, it is not so. Now it is over, but next Tuesday, okay, when we shall meet each other again, I'm going to show you why actually not only it is not necessary to consider all the infinite bands of the semiconductor, but actually it is sufficient to consider only two bands. Two bands of the semiconductor are sufficient to describe the electrical behavior of it, and of course they are the two bands that are shown in this figure. But this is not obvious, so I'm going to give you the explanation next time. So for the moment we stop. If there are questions, you may just ask them. Otherwise, we see each other next Tuesday.